Okay, let me check. I think this should be dx over dt, sorry. If you want to check, you can check and change x into 15, and then check if this is 4, and then equal to 1 over 5. Should be, it's going to be similar with this, I think. Okay. Okay, any questions from these two questions? From this example 4 and 5? Okay, probably next Tuesday I will go back to review some questions on related rates. Okay. But now I will try to move on to the next sections, which is probably the last one of the last sections in the chapter 3. And by the way, we will have next quizzes maybe on 29. Okay, 29. The morning, Tuesday, 29. So before the long holiday in the first week of April. So 29 March. Okay. So let me write here. March 29. This will be quiz 2. Topics will be chapter 3. Chapter 3 will include the techniques, all the trigonometric, a power rule, a logarithmic, the inverse trigonometric, they will be included. Also, maybe related rates also includes. And the last one here, the near approximations. Of course, because there are too many, at least some representations from each part will be on your quiz. Maybe 6 to 7 like last quiz. So maybe 6 questions or 7 questions. Just like last one. Okay, now let's move on to the next session. This is the linear approximations, or we call the differentials. Okay, now we start by looking back at our curve. This is just a random curve. Let's say we have the y equal f of x, and then we have a tangent, maybe here, a tangent there, let's say this is, I will write this tangent as a equation of line L of x. Okay. And let's make a point, a tangent, equation of tangent, and then this is point of A and f of A at this particular point here. Okay. And from what we learned, or from the study that have been done before, we know that your line equations will be y minus y1 slope and then x minus x1, right? So we are just taking times to remember this line equations. And then from here, what I want to show you is we are going to use some, we are going to use the slope or the tangent to take approximations to our curve. And if we check here, and if the point is on this A, this is x, y, right? So if x, y, the point is at A, f of A, we are going to have y minus f of A equal, we know that the slope is our tangent, which is our first derivative, right? Okay, that should be clear. So we can write this as f prime at x equal A. Okay, I hope you don't get confused here. And then x minus A. Okay, then I can write this in terms of f of A plus f prime of A and then x minus A. Okay. And now this y equations is our line equation, that is L of x, right? So we can write y as L okay. Now we can call this L as linearizations. And what does that mean? Okay. Now, to help you to understand what we are doing here, then look at this point here. If you draw with maybe quite sharp pencil or pen, maybe you will see that, or maybe in your paper, you can see clearly that this tangent line is touching exactly one point here. That's the definition of tangent, right? But sometimes, if you draw in your paper, or maybe you see graphs on the some graphing calculators, you will see the pixels, right? Pixels. Like you have, like for example, for my case, you see that it has the. Let me go zoom here. You see that it's, if you go and see from the from this surface here, is having some pixelated graph like this. Like when you're taking the photos and you zoom in, sometimes you have like a rectangle like that. Okay. We call that a pixels. The more pixels you have, the more clear your picture will be. So that's why you have like how many megapixels your camera and your smartphone has. So the more pixels that camera have, the accuracy of the details on that picture will be more clear. Right? When you zoom in, it's still clear. Zoom in, it's still clear. But you also, maybe you have learned also an image using a vector. You know design or graphics. Vectors means they don't have pixelated scale. So when you draw and you take time to zoom in, they will always perfectly align, no pixels. Okay? But when you have kind of like a triangle like this. It means that it has a pixelated, it has a scale. Okay? Now, imagine that this line and this curve, you're trying to zoom in, okay? And maybe you are zooming nearby this point, okay? Maybe over here. Can you notice any difference? If you observe this one and this one, you see the gap, right? But can you see the gap here? No, right? So that's why with this out, I can approximate what my function will be. Okay? So I can approximate the f of x as long as it is close enough. Okay, close enough. So we call this terms linear approximations. Approximation. Or usually maybe tangent line approximation also okay, but I think just linear approximation will be fine. Okay, maybe I'll give you okay, so for example, if I take a function that is, maybe start with the easiest one, like square root of x. Okay. Or maybe not this one. Maybe taking maybe this for, okay, maybe that will be more. We want to know what is this number will be without calculators, okay? Without calculators. So if you don't have calculators, can we calculate this easily? Okay. Now imagine that if you can make any functions out of this 4, okay, 4.1. First thing, maybe we can think the functions. Maybe this function is square root of x. Maybe that will be simple enough. Okay? Maybe let's try to have our function as square root of x. Okay. And now the key for this linearization to be work, okay, we need to have this a, right? A means, to help you get more practical, A means any numbers that is easy for you to work with. So meaning, when we have maybe find something around here, and we know that we can find something here that is, which is our slope or our tangent point, using a's is much more easily, then we can have, like maybe if we have here another number that is maybe difficult number, or maybe we need to configure, determine what is this, and by using the same tangent, And because we are dealing with this linearization, because it looks similar, and we can try that as well. So meanings, we can try that A probably 4, because we can get square root of 4 2. So f of A is just square root of 4, which is 2. Okay. And then the other component, because we want to have 4.1. So there are certain a delta, right? So a delta x will be 4.1 minus 4, which is 0.1. Okay. Now the other component that is still important is the f prime 4. Or maybe let's try f prime x first. This will be 1 over 2 square root of x. This is from the square root of x we derive. This is our result. Okay? Now, if we take the a, which is 4, and take into our derivative, we get 1 over 4. And thus, we have Lx, okay, f of a plus f prime a, and then x minus a. This will be the delta x, right? So, or we can write f 4.1 is approaching fa is just 2 plus 1 over 4, and then this is 0.1. Or we can get this number as 2 plus 1 over 50. 1 over 40, sorry. Okay, so by doing so, we can take this linear approximations, and then we can calculate any numbers that is still difficult for us. Maybe square root of something, maybe 5.3 with power of 4. This is also possible. Which means maybe we need to think what kind of function is this that we can relate to these numbers. Okay? And if we don't have calculators, what can we do? First application of linear approximation is to calculate some algebraic, some terms in math that maybe you can relate to the derivative. Okay? So, yeah, I do hope you get to have some understanding with this. Okay? The key point is, again, nearby this point, all looks the same. That's the key point. Okay? All looks the same, which means that you have unknown point here, as long as you know this a of and f of a, and you can take this number easily in your calculations. You can also calculate number here and here and here. Okay? Okay. So as I mentioned before, okay, distance of SR is f prime x dx, which is dy. So dy represents the amount that the tangent line rises or falls. This means that the change in linearizations. And delta y represent amount of curve y equal f of x rises or falls when x changes by amount of delta x or dx. Okay. Okay. So I hope this can clearly show you that this is our main curve. Okay, our main curve. So if we add this x with some delta, or in our case we can also consider the delta as our dx. We will look that we have an actual delta here, which is our delta y. But if we are thinking in terms of differentials, it's actually this dy. Okay? So it has some gap here. But of course, in terms of differentials, this gap is really small. This gap is really small because this is actually we are consider this delta as our d, which means it's supposed to be small. Okay? So when we have something small change to deal with, okay? Maybe some changing in some decimals. Okay? So for some curve, we can think by using this differentials. Okay? So, for example, if we take the values, okay, for example, let me take it into the new example here. So compare values of delta y and dy if the y equal f of x is equal to x cubed plus x squared minus 2x plus 1, and x changes from 2.05 to 2.01 or maybe 2.205 first. 2.205. Okay. Now, what this comparison means is, first we take x equal 2, and we are going to look on what we are having. This is just 9, right? And when we have f 2.05, you can check with your calculator. But let me just write this down for you. This will be 9.717625. And thus our delta is the difference between these two, f 2.05 minus f2, which is 0.717625. Okay, this is our delta y. But our dy, if we take this f prime x dx, if we take derivatives, okay, this means that we are having 3x squared plus 2x minus 2 dx, right? So when x is equal to, and dx, or our delta, is 0.05, which is from 2.05, so the delta will be 0.05. This dy becomes 2 squared plus 2 minus 2, and all will be multiplied with 0.05. And this will be resulted in 0.7. Okay, so what I want to show you here is the way we are looking at is we can have that delta and dy. We have a small decimal difference, right? small difference. Okay. So which means that we can take this approach to define an error. So if we have a function and we want to have like maybe we change the distance, we are going to have like a difference in error. Okay. So we have like different in decimals here. Okay. So in this case, we can also use this logics of the differential when we are dealing with, if we want to find the maximum error. We can have the maximum error. It depends on maybe if you would like to use some maybe formulation in area or volume or anything that can be formulated into our differentials. We can measure the difference between the delta and then the differentials. Okay. Now, if we have this is changed from 2 to 2.05. If it is changing from 2 to 2.01, okay, we can also take this approach. Then we can take some time to evaluate. So the result is 9.1 for f2.01. So delta y is 2.01 minus f2. This will be 0.140701. Okay. When dx is 0.01, we will have dy 2 squared plus 2 minus 2, and then multiply with 0.01. This will result 0.14. Now we have also difference in decimals. Of course, if you compare, it's having 0.01 difference. This one. Left one, we have 0.0007. Okay? So which means the smallest distance, we will have smallest error. Okay? This is just to give you an idea on how we can apply our linear, the line, or in our case the tangent, okay, the dy here, and then finding out how many errors we have, or how much error we will produce from these two comparisons. Okay. So we can also write from this two that we can write that fa plus dx, this will approach f of a plus dy. Or maybe we can write completely that from the first time we learn the linear approximations, we will have this terminology, these terms. And we can simply rewrite f prime and make it into dy over dx. Okay. So dx is x minus a. So x is a plus dx. Okay. Okay, this is what we have before, and we can also rewrite in terms of differentials. So usually, questions related to this differentials is usually you will be comparing the actual delta, and then you need to compare with the d that you are going to have as in the differential. Okay, and for 3.11, the hyperbolic functions, I think we will not really deal about that. Okay, but you can, if you want to read about that, you can learn. Okay, so hyperbolic functions. Its function is not really that much actually, but the hyperbolic function, it has the same property as your trigonometric. Okay. For example, sine hyperbolic is similar to sine. So when you have a derivative of sine hyperbolic, which means it will be a cosine hyperbolic. Okay. Well, of course, it's not trigonometric, but it has the same property as trigonometric. Okay. So they propose that they name sine or cosine hyperbolic because they have the same property with trigonometry. But we are not really going much details for our course, and we will skip that. So 3.11 we will skip. So we will just end on this 3.10 for chapter 3. Okay. So later on for the quiz, next quiz, 29. On 29, we will just focus on the chapter 3 until 3.10. Okay? So we skip 3.7, 3.8, and 3.11. Okay, so that is not really needed. So let me write here. Okay. So chapter 3. So I will just write the skip one. Okay. So skip 3.7, 3.8, 3.11. 3.7 is, I think, the exponential, the decay or rate of change in physics, I think. So this means that we don't really need to learn more details, so we skip that. So March 29, we will have quiz on chapter 3, and probably maybe next week, or maybe before we have the quiz, I will have some time to review and maybe some small homework, but not really like you are writing in your paper. The homework will be based on the online platform. I will design, and if I have time, I will make it for you, and you can have some time to solve the homework. Okay. So I think that will be for today's class. Okay. So I think I will